we're going to start getting to the moment where basically those of us who are taking the AB exam, okay, cool. Those of us who are taking the AB exam have the stuff that we need to keep looking at. Sorry, back up. The people who are taking the BC exam have the stuff that they and us need to keep looking at, and the people who are taking the AB exam are essentially done with reviewing material, and they're just practicing and going back and solidifying those weaknesses. Today is actually a day that's a little bit of a split. Those of us who are in here in this room right now, if I do a quick look, all of us in here are taking the BC exam, so we can work through everything together. But those of you who will be taking the AB exam, I will go ahead and sort of indicate what things you need to do as we go. Because this video I'm recording with students here to be able to ask questions, but for those of you who are in the AB test, I will tell you and indicate what you need to do at different times. All right, let's go ahead and get started. You'll need your AP Review 10 packet. We're going to be talking about applications of integrals, mostly applications of integrals in context. So if we have actual real life situations we're working with things, that are changing. But at the start, to provide us with some continued practice at some challenging questions, I want us to take a look at a question. It says BC 2004, wasn't the BC exam, but it is a question that is good for both AB and the BC test. All right, and I want us to do the following with it. I want us to get a chance to essentially try some things on your own and then get some feedback. So what I'm going to ask you to do is go ahead and I want you to read through this question, write any notes and annotations that you want, and I want you to go ahead and do just part A right now. Pause the video, we're going to start working, and then come back and check your work. Fine. I'm going to call on some people to help out along the way today to help us with some reminders, okay? I will dictate the problem, then I'm going to call on somebody. The figure above shows the graph of f prime, the derivative of f, on the closed interval -1 to 5. The graph of f prime has horizontal tangent lines at 1. Maybe it can help to draw one in, horizontal tangent lines. At 1 and 3. And f is twice differentiable with f of 2 is 6. That, to me, sounds like an initial condition. Let me just make myself a note. I note the x-coordinate of the point of the graph of f. Give a reason for your answer. So let's start with that reason for your answer. If I could come off the microphone for a second, let's have Quay, since she wasn't with us last time. What do we look for on the graph of f prime to figure out where there's a point of inflection?
A point of inflection happens where f double prime of x changes sign. So on the graph of f prime of x, we want to see where the slope changes from positive to negative or negative to positive.
Great. So going back to those definitions there, right, like Quay just did, that point of inflection is when f double prime, and you can even write yourself like a little note, f double prime, in parentheses, the slope of f changes sign. All right. Raphael, at what x values is that going to happen? Where does the slope of f, or f double prime, sorry, the slope of f, I didn't even finish right, the slope of f prime, what that should say, slope of f prime, where does the slope of f prime change signs, Raphael? At what x values?
So 1 and 3.
1 and 3, yes, because we think the second derivative is changes sign is what we want. This is the first derivative. The second derivative is the slope of this graph. So as the f prime graph is increasing, f double prime is positive, then f double prime is negative because f prime is decreasing. So there's a point of inflection at x equals 1. And then our other one, hey, look, our f prime slope is negative, then our f prime slope is positive. So that means the second derivative is negative, then the second derivative is positive. F prime goes from decreasing to increasing. There's another point of inflection at x equals 3. Very good. Always jump in with questions if you have them. I'm happy to help out if we don't cover something you have a question about. B, at what value of x does f attain an absolute minimum value on the closed interval? At what value of x does f attain its absolute maximum value? Show the analysis that leads to your answer. Nemin, I want you to jump on here. When we're dealing with absolute minimums and maximums, what points do we look for to be able to do that kind of analysis? This one's not a theorem. There's sort of a process or like a set of steps we go through to find absolute minimums and maximums, and they involve first identifying two kinds of points. What kinds of points do we look for that could be absolute minimums and maximums?
The endpoints?
The endpoints?
And then the critical points.
Perfect. And the critical points. Whenever we see this kind of language, those are things we need to look for, okay? So let's go ahead and do that. We're going to do this one together, endpoints and critical points. So that part stays the same. And our critical points, looking at the graph, will be the things we identified, x equals 1 and x equals 4, because those are the places where the derivative has a 0. And our endpoints will still be the same, x equals -1 and x equals 5. So none of that stuff has changed. That's still what we need to sort of do some thinking about. What I'll try to do is talk through my thinking in this problem as if using a different strategy maybe is the best way to make sure I get my right notes. All right, so let's actually ignore this whole x is 2, f of 2 is 6 thing. Let's just kind of ignore that for now. Let's just deal with only this this derivative graph thing. Okay. Let's say that I wanted to know what happens as I integrate along this graph. Because I do, in the end, want to talk about f. So f is going to be the integral of this thing, no matter what. So there's no way around the whole integral stuff that I have to do. But let me think about it this way. What if I just took the integral of f prime from -1 until somewhere in here? I can stop anywhere along here. If I did the integral from -1 until this critical point when x is 1, -1 to 1, if I did that integral, it would be negative, right? Because the graph's below the x-axis. Follow me?
Yeah.
If I kept going, the integral from -1 until 4, that integral is still negative because f prime is below the x-axis, right?
Mm-hmm.
Which integral would be more negative? The integral from -1 to 1 or integral from -1 to 4?
Wouldn't it be -1 to 4?
Exactly, right? The integral from -1 to 4 would be more negative because there's more space underneath the x-axis. So what we can say is, and we know this because the derivative graph is below the x-axis. The derivative graph is below the x-axis means the original graph is decreasing. So f is just decreasing this whole time as I run along this graph until this spot right here. I'm just going to write that down. I'm going to say f decreases from -1 to 4. So at x equals 4 is the Does that make sense?
Yeah.
So that could be one way to sort of simplify that whole process. But that doesn't help us answer the question about the absolute maximum. That's a little trickier, right?
Mm-hmm.
The absolute maximum could be where I started. The absolute maximum could also have been, well, we know it's not there at 2 or at 1 because that's I'm getting a lot of lines, so let me get rid of that.
Oh, I think your screen is frozen for me.
Oh, how about now? I erased some stuff and I'm drawing a new point.
Okay, now it's working now.
So if we're talking about the maximum stuff, it's a little trickier. I know that the maximum can't be at 1 because we already said that's just decreasing. F is just decreasing. It can't be at 4 because we also said f decreases up till there, and that's the minimum. But the maximum could be over here at 5. But the maximum could have also been where I started. You know what I mean?
Yeah.
So that's where I got to do a little bit of actual sort of like heavy duty calculus thinking. Here's one way we can do it different than what I said earlier. Let's, you know how we have the fundamental theorem of calculus that says the integral from -1 to 5 of f prime of x dx is going to be equal to the antiderivative, so f of 5 minus f of -1. You know how we have a rule that says that?
Yes.
Well, let's think about if this could be useful then, because f of 5, do I know what f of 5 is? No, I don't. Do I know what f of -1 is? No, I don't. Yeah, actually, why did I do this? My mind went to this spot. Why did I come here? There was a reason. Hold on. Sometimes I get lost in my own thinking. Oh, yes, I remember what it was. Okay. So if I think about this whole integral, then -1 to 5, I'll do that in orange. Talk to me for a second. If I did the whole integral across this whole thing, would the value come out to be positive or negative based off what you're seeing in this graph?
I think it would be negative.
Yeah, like we have a lot of negative space down here, here, and like some positive space, but not what's down here, right? So what do we? That means that this value over here is less than 0, right?
Right.
What does that mean for us? Well, if I kind of rearrange this inequality, I add f of -1 to the other side. That means f of 5 has to be less than f of -1. Follow me?
Yeah.
So what does that mean then? If this is true,
If that's true, then
where's the max?
maximum would be -1.
Exactly. And then you could say, okay, maximum is at x equals -1. I want you to go ahead and try C on your own. This one I bet you can do. It says let g be the function g of x, which is x times f of x. Find an equation for the line tangent to the graph of g at x equals 2. All right. Take 2 minutes to give that a shot. All right. Even if you're not totally finished, I want to pick up the pace a little bit. Jessica, what things do we need to write the equation of a tangent line?
We need a point and a slope.
Okay, so we definitely will need a slope. That sounds like a derivative thing. Stay on for a second, Jessica. What derivative rule will we need to be able to take the derivative here?
Product rule.
Exactly, and that's actually most of the points for this problem is just doing the product rule properly. We need the derivative of g to find the slope. We keep the first, derivative of the second, plus derivative of the first, keep the second, and if you did your derivative correctly there, that's 2 points, and you get 1 point for doing the tangent line correctly. So what do we need? We need to find g prime of 2, so that'll be 2 times f prime of 2 plus f of 2. And so, Nema, this is actually where f of 2 becomes important. We need that number because 2 times f prime of 2. Well, f prime of 2 we get from the graph. F prime of 2 is -1. So 2 times -1 plus f of 2, which was 6. That'll give us 4 as our slope. And then g of 2 is 2 times f of 2. F of 2 we saw up top here was 6. This will be 2 times 6 will give us 12. That's our 0.2 comma 12. So we end up with y minus y1 equals mx minus x1. These kind of like function notation derivative questions are something I think you should be ready for as well. I realized maybe one other way you could get into that part B, I know my explanation became kind of convoluted as I worked, is just to look at the graph and say, okay, well, what does this derivative tell us about f? Well, the derivative graph tells us the slope of f. So as long as I'm below this line, f is decreasing. As soon as I get above the line, f prime is positive, f is increasing. So as long as this graph is like down here, that means F is decreasing, which means the minimum has to be over here at 4. That could also help if you were stuck. All right. So let's take a look at now. If you are in AB, you can stop here and jump down to the homework problems. They're a little different for you, so read carefully. For BC people, we are going to move on to look at one other type of question we got to keep in mind around applications of integrals. And those are the ever popular and ever fun rate in, rate out problems. Hooray! Now these are ones that are really hard to find non-calculator questions. So I'm not really a betting man, but if I had to guess, my guess is that there will probably not be a question like this year, at least in the way that we typically see them. But we should be ready for them in case they give you something, because this FRQ, although it was a calculator FRQ, was very, very close to being essentially a non-calculator FRQ the year this one came out, all right? Some of this you can already just do on your own, though. So what I would like you to do is actually go ahead, read through the question, and I want you to go ahead, pause the video, and do parts A and B, okay? Do parts A and B, please. You don't have to simplify. I know I'm asking you to do this without a calculator. If you have a calculator, you can do it with a calculator. Do parts A and B. You don't need to worry about simplifying. All right, so check your work against what I'm about to do here, and then jump in if you have any questions. We want to estimate R prime of 2. We're given a table here that gives us the rate at which water leaks from a tank, and there's R of 2. This is R of T. This is my favorite kind of problem where I have to say water and water over and over again, right? So the water's leaking out of this tank. We want R prime of 2. It's somewhere in here. So to estimate that rate of change of R, I can do R of 3 minus R of 1 over 3 minus 1. What are my units for R? They're liters per hour. Liters per hour. What are my units for 3 and 4? It's hours. So all I have to do is plug in the numbers. I don't even need to simplify. I could have just said 950 minus 1190 over 3 minus 1 liters per hour per hour. So find the rate of change of a rate, it's liters per hour squared. Turns out it's negative 120 if you simplify that, negative 120 liters per hour squared. You did need to include the units there. So if you did not do that, you would have lost that one. Liters per hour squared. B says use a left Riemann sum with 4 subintervals indicated by the table. Hey, look, here's 4 subintervals, 0 to 1, that's a delta t of 1. 1 to 3, that's a delta t of 2. 3 to 6, that's a delta t of 3. 6 to 8, that's a delta t of 2. So my left Riemann sum, remember, Riemann sum approximates an integral. So the integral from 0 to 8 of R of t. We're trying to estimate the total amount of water removed from the tank, right? Because the integral of the rate at which water is removed will give us the total change in the water, or the amount that has been removed, all right? Because RT is just measuring the removal. But it's an approximation, so I'm going to say it's approximately a left Riemann sum. So I want to multiply the delta t by the left-hand height. That's the base of the rectangle times the left-hand height of the rectangle. So 1 times 1340 plus 2 times 1190, 3 times 950, two times 740. Remember, the units work out for this because 2 would be hours. So we're talking about 2 hours times 740 liters per hour. So 2 hours times liters per hour will give us liters, an amount of water, a volume of water that's leaked out. So here's that. This will give us liters in the end. If you do simplify that, you do get 80, 50 liters. But there's more to this question. So that's the left Riemann sum approximation for the amount of water removed. Is this an over or underestimate of the total amount of water removed? And give a reason for your answer. All right. Here, let me ask, Ooh, I lost something here. Okay. Let's do Stephen. How can we determine whether or not this approximation is an over or under estimate of the actual amount of water removed?
First, we want to look at the trend from RT, and then if we look at it, we see a trend of it decreasing. So we know that if it's decreasing, that means, and we're using a left Riemann sum, then it's going to be an over approximation.
Right. So all we have to say is exactly that. RT is decreasing. We have to say what it's doing, and it says in the problem here it's decreasing too. RT is decreasing, and a left Riemann sum was used. And the left Riemann sum was used. Therefore, my approximation is, and if you want to think about this graphically, the graph of RT is decreasing, and we used a left Riemann sum approximation, so my left rectangles will be an over approximation. Is an over approximation, or an over estimate. So part C and D get into the stuff that is related to our applications of integrals and context, though. So what does C say? Use your answer from part B to estimate, to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So this is where we need to do a little bit of thinking. I'll leave that back up while we're thinking. The amount of water in the tank. Well, here's the thing, right? We have this tank of water, and I like to do little diagrams. We got a tank of water. It has some water in it. We do know at time t equals 0, there is 50,000 liters of water in the tank. So there's actually water in there at the beginning, right? And water is being pumped into the tank at W of t. And then water is also being removed from the tank at R of t. Those are rates. So if we want to measure the total amount of water in the tank, we have to take all of this into account. So here's our reminder. For these total amount problems, if we're measuring the amount of something, we'll call it A of t. It is going to be equal to the initial amount plus the integral from A to t of the rate in minus the integral from A to t of the rate out. Because the integral of the rate in will give us the amount that comes in. The integral of the rate out will give us the amount that went out. And if we add the amount in and subtract the amount out, then we'll get the amount that's actually left in there. We take all the ins and outs into account, right? That means that the rate of change, sort of a conclusion of this, is that the derivative of this is just going to be the rate in minus the rate out, but that makes sense. The overall rate of change is the difference between the rate in and the rate out. That's kind of our big idea here for these rate in, rate out questions. All of our conclusions can come from that. So let's do that for this one. Use your answer from part B to estimate the total amount of water in the tank. So the total amount of water is going to be approximately my initial amount, 50,000, plus the integral of the rate in. We know the rate in is W of t, so it's the integral from 0 to, I want to approximate at the end of 8 hours, so 0 to 8, W of t dt, whatever that integral will be, minus the amount we lose, which we calculated in B. It was 80, 50, right? So this expression will give us the total amount still in the tank, 50,000 plus the amount we gained minus the amount we approximated that we're going to lose. We're not actually going to calculate this right now because that'd be something you would have to plug into your calculator, and we're not going to see questions like that this year. But this would be the setup, especially if they ask you to write an equation. Right. And the last question, pretty good one. From 0 to 8, is there a time when the rate at which water is pumped into the tank is the same at which the rate at which the water is being pumped out of the tank? So, how do we approach this? This becomes kind of interesting here. Let's see. What do we know about the rate in? Well, let's start with just like the rate in, R of 0. Well, we know the rate coming into the tank at the very beginning was like 1340, right? The rate coming R of 8 was 700. What about the rate coming in? At the beginning, W of 0. What's W of 0? W0 would be 2000 e to the 0. Okay, that's just 2000. And then at the end here, at the end of our 8 hour, W of 8, what is it going to be? It's going to be 2000 e to the, I'm going to plug 8 in here, so it'll be negative 64 20ths. We're going to cheat a little bit because this is one of those things that it's like, this is a calculator active question. So I will help us out here just to help us practice the calculus idea. 2000 e to the negative 64 20ths is about 81. So here's what I observe. W is going to go from 2000 to 81. Right? R is going to go from 1340 to 700. At the start, W was bigger than R. At the end, R was bigger than W. So these graphs at some point, if W started off bigger, at some point, R and W are going to cross. Because W started bigger, it was 2000 at the beginning compared to 1340. And at the end, R was 700 compared to 81. So what theorem can we use to talk about how this is going to work? And we have a point where we have to cross here. Jeannie, what do you think? What theorem can we apply here to prove or to state that we are going to have a place where these two functions actually touch? Oh, Jeannie's not in this. I thought she would have joined us. I'm sorry. Let's do Nina. Can you take a second away from your other thing? Yes, this does sound like an IVT thing. Essentially, what we need to say then is that if W of 0 is greater than W, not W, oh my gosh, is greater than R of 0, and R of 8 is greater than W of 8, and R and W, do we know that they're continuous? Because we need to know that for IVT. Yes, we do. They're differentiable here. Yeah, and R and W are continuous. Then R of T equals W of T on 0 to 8 by the IVT. So for this one, you have to consider this comparison here and then answer it with your explanation by IVT. Here's what I'd like you to do then. We've kind of walked through 2 FRQs. What I would like you to do is, if we'll look at the next one. What I'd like you to do, this was a legitimately non-calculator one, okay? I want you to read through this free response question, okay? And answer parts A and B, okay? Just parts A and B right now. Go ahead and do that. Take 4 minutes to do that. and that's where we will include. Okay. All right. What I would like to do is, having read through the question, knowing this is kind of rate in, rate out situation, it kind of makes sense. We're giving something about 700 people in line, 800 people move out of line. RFT is the people moving into the line. If I could get, let's see, Madison, for part A, what integral could you write that would determine A for us? Yes, I bet you did use the graph, so I'm asking a slightly different question. If you had to use an integral to represent what you did on the graph, what would the integral be? The integral from blank to blank of what? The integral of r of t from 0 to 3, yes. And here's why, right? If we want to know how many people arrive, r of t is the rate at which they're arriving. So the integral from 0 to 3 of r, that's not going to be an r, of r of t dt will do that for us. That'll find us the amount of people who arrive, how many people, not a rate, but how many people arrive, 0 to 3. That means we need to use this graph and find that integral right here. So you can chop it up. You have to find the area. You can chop it up kind of however you want. You don't need to simplify it, but that integral, all of this area is what we needed here up until x equals 3. It turns out to be 3,200 people. You add on the rectangle, 2 triangles and a rectangle. 3,200 people. That's a weird way to do people. All right. B, is the number of people waiting in line increasing or decreasing between t equals 2 and 3? This one I'll take a volunteer. How can we start answering this question? How can we determine, based off the information in the paragraph and the graph, whether or not the number of people waiting in line is increasing or decreasing? All right, then we call away. Quay, what do you think? We look at r prime of t. So r prime of t is the rate at which people are arriving. R prime of t, the slope of this graph, would tell us how the people, whether or not the rate at which people are arriving is increasing or decreasing. We want to determine whether or not the number of people waiting in line is increasing or decreasing. So let's actually first, maybe this will help. Maybe let's just write an equation that would determine the number of people waiting in line. Let's write a people formula. So the amount of people waiting in line, call it A of t. The number of people waiting in line is how many were there at the beginning? 700. Plus, we would add on how many people are arriving. So the integral from 0 to t, we have a rate at which people are arriving. Yeah, the people move into the line at a rate. So that's the arrival rate. That's the rate in 800 dx minus the rate people are coming out. So the integral from 0 to t of r of x dx. But we want to know, so this is an equation for the people waiting in line, but I want to know, is this thing increasing or decreasing, right? So if I took the derivative of this, that will tell me, the derivative is the slope. So the derivative...
Mr. Markwalter, yeah. I disagree with your thing, because isn't the people who are arriving at the ride the graph of RT, while meanwhile the people who move onto the ride, so they're no longer waiting in line, the 800?
Sorry, yeah, I got my signs wrong here. Thank you. Sorry, yep. Minus, sorry. We lose people at 800 and we add people at the rate on here. So we can take the derivative of this. This equation measures the people waiting in line. If I want to figure out if this is increasing or decreasing, the derivative will tell me that. But the derivative of any of these accumulation things, derivative 700, 0. The derivative of this thing over here is going to be negative. The derivative of an integral is just the thing on the inside, negative 800. Plus the derivative of an integral will just give us r of t. Really, the rate of change, if I want to determine whether or not the amount is increasing or decreasing, all I care about is the rate in and the rate out. In other words, I need to figure out which one of these things is bigger, right? Which of these things is bigger? Between 2 and 3, is negative 800 bigger than r of t? or is negative 800 less than r of t? Because if the rate coming in is bigger than the rate going out, then the line's getting bigger. The number of people in line is increasing, decreasing. So let's see, between 2 and 4, what do we know about r of t? What do we know about between 2 and 3? Between t equals 2 and 3, what do we know? Well, look, it looks like r of t is bigger than 800. You can even just draw a line here. That's the rate at which people are leaving. R of t for the interval asked about is bigger than 800. So I can say r of t is greater than 800. So I guess just to say it's greater than 800. Therefore, as r of t is the people coming into the line, the number of people in line is increasing. Does that kind of make sense, doing this comparison of the rates at which they're coming in and out? That's ultimately the thing we need.
Can you have also done A of 2 and A of 3 and just said that it increased or something?
Yes, only because though we're dealing with linear piecewise functions. Because if this graph had been anything more complicated, that might not necessarily have been true. Because if you just find two endpoints, you don't know what's going on between those endpoints. You know? So what I was going to do for those of y'all who join me for live stuff, you're free to go. I am going to finish this problem so I can post it. If you want to work along with me, then please do. Otherwise, for homework tonight, what you would need to do is for Thursday night, there is for BC people, there are 2 FRQs, one here. I like this one. It's a nice sort of complex looking derivative question. And then one that's another rate in, rate out question. This one you can use a calculator on. It was originally a calculator question. So that's the homework for Thursday night. For BC people, for AB, you gotta do the first question, and there are 3 concepts to do for AB testing. So thank you for joining. I will continue through this question for those people who are wanting to work through it. I do recommend taking some time with it, even if you put this video on double speed. People who are here joining me live in studio, as Quay said, feel free to go whenever you want to, but I will finish this and then stick around for questions. Right. C. At what time T is the line for the ride the longest? How many people are in that line at that time? Justify your answer. Talk to me in the chat box. At what time T is the line for the ride the longest? What does that sound like or cue in your mind? What kind of calculus idea do you feel like this question is asking us about? Steven says absolute max. Any other thoughts? Yeah, that's what I'm thinking too, absolute max. Because longest, yes, exactly, Clay. Longest sounds like maximum thing. And we want the maximum number of people in line. So basically, we're trying to maximize our A of t equation, which I'll just copy that back down here. I know I messed it up the first time. We'll get it right this time. Was 700 plus the integral from 0 to t of r of x dx minus the integral from 0 to t of 800 dx. So we want to maximize this thing. All right. So we've done maximum things before. We need critical points. We need endpoints, right? Endpoints are relatively easy to find. T equals 0 and t equals 8. Right, t equals 0 and t equals 8. The critical points get a little tougher. So critical points. Critical points, I need the derivative of a, so I need a prime of t. Derivative of that, so derivative of 700, we've done this before actually. Derivative of 700 is 0, derivative of the integrals, that will give us r of t minus 800. We're looking at the rate of change formula. The rate of change, the a prime is the rate in minus the rate out, right? So what do I look for? Where is a critical point? This is when this thing is equal to 0. In other words, where r of t equals 800. All right, let's look at the graph up here. Here's the graph of r of t. Well, I guess it should be lowercase r. I keep writing uppercase r. It should be lowercase r. I apologize. So we look at our graph. And we go, okay, well, where does r of t equal 800? We can figure that out pretty quickly. Our graph equals 800 right there at t equals 3. So we have all of our values now. You get 1 point for thinking about t equals 3. Then we gotta do some work here, right? It's actually kind of like that hypothetical situation earlier. So to figure out the actual value, of like what's going on here, we can do a couple things. One, our rate people are coming out is at 800, right? So up until this time, what do we know about the rate in? R of t is bigger than the rate out up until 3. So for this section, since R of t is bigger than the rate out, the line is growing, right? Down here, R of t, this whole section down here, R of t, the rate in, the rate out. So the line is shrinking. And so we can use that if we want to in our explanation. We could also, if we would like, and if we actually want to take the time to do it, actually calculate these values. So for example, we could say a of 3 is 700 plus the integral from 0 to 3 of r of x dx minus the integral from 0 to t of 800 dx. We could figure that, oh, that should be a 3. So that's 700, the integral from 0 to 3, we already found in part A was 3200, minus the integral of 800. We have a shortcut for these constants. It's 800 times 3 minus 0. 800 times 3, that's going to be minus 2400. It's going to mean at A equals 3, we have a total of 1,500 people in line. That's a long line in the amusement park. Not even it would be Disney. All right, at the beginning, at t equals 0, we knew that there were 700 people. Then we go, well, what happens when t is 800? Well, we go, hey, we don't even need to worry about t is 800, because when t is 800, sorry, t is 800. When t is 8, we don't even need to worry about it. It can't be the maximum, because when t equals 8, the people entering the line is less than the people leaving the line. So the line's not at a maximum. The line's decreasing. The rate in is less than the rate out. So I don't even need to worry about it. So I could say at t equals 3, the line is at a max. The line has a max of, what do we find, 1,500 people. Wow. And finally, write but do not solve an equation involving an integral of expression r whose solution gives the earliest time t at which there is no longer a line for the ride. Okay. We want an equation involving an integral so that there's no longer a line. This is actually really easy for us to do, right? Because we already have an equation for the people in the line. Actually, back up. The equation for the people in the line is already written here. Save some time. the equation for the people in the line is right here. And we want to know, write an equation so that there are no people in the line. So all we actually have to do, part D, is say 700 plus the integral from 0 to t of r of x dx minus the integral from 0 to t of 800 dx equals 0. This is an equation involving r, involving expression r, integral expression of r, I apologize, whose solution, if I solved for t, would be where there's no one in line. Okay. I'll stick around for a few minutes if y'all do have questions. As a reminder, the homework is there. It's 2 free response questions. One that's about analyzing a derivative graph. I really like this question. It has some really interesting kind of quirky work you have to do in here. Don't freak out about the symbols and things. Trust what you know for the definitions and just go with that. And then rate in, rate out problem you can use a calculator for. I'll stick around if y'all have questions. But other than that, thanks for being here for a little while.